Here's some more examples for integration by parts. So the first example shows using parts twice, because sometimes once is not enough. So here's a typical example: x squared sine x. You go for knocking down the x squared. That's always a good strategy to get something simpler. And of course the v prime, natural choice to use sine, because the sine and cosine are going to toggle back and forth. So that's always a good thing. So it's u v minus integral of v u prime. Alright, so that comes out to be this, plus I factored out the 2 out to the front, took care of the 2 negatives to be a plus, and now I'm zeroing on this integral here. That's not a substitution, it's another parts problem. So writing it in a different color would be a good idea, or putting it off to the side, another part of the paper, so you can accomplish that integral now. So I'm just going to keep it in red here. Integral of x cosine x. So your natural choice is x is for u, since it knocks down to 1, and the cosine and sine toggle back and forth, so that's always good. So you have u v minus v derivative of u, and now you can accomplish that integral, and you're just going to have this. Notice I put a c1, c sub 1, because later on in differential equations your c's are going to matter what they are. So I like to have a c1 sitting here for the constant that comes out of this integration, and then later on we'll change it back ultimately to a c. So the subtraction of the negative becomes positive. So that's what we have so far. Now we return back to the original problem, which is integral of x squared sine x, and that was equal to this step here. And now we're substituting in for what we found here, substituting in this. That's what was found. And now when you distribute the 2 in, you see that 2 times c1 becomes c. Just a little detail there. And then here's your full answer here. I checked that with Wolfram Alpha, and the integral of x squared times sine x really is 2x sine x. That's this part. Subtract x squared cosine x. That's here. A minus subtraction of another subtraction there cancels out to be a plus 2 cosine x. That's here, and the constant's here. So that works. Here's another example where sometimes you have to use substitution during a parts problem. So here's a classic: arctangent x. So we're going to invent the 1 in here for v prime equaling 1. So you have arctangent x times 1. So you can, just see that being put in there. Okay, and then you can take the derivative of arctangent is 1 plus x, 1 over x, x squared plus 1, and the antiderivative of 1 is x. And that's usually, it's not good to go up when you're doing this, but what you'll see is that by getting this integral here, you'll be able to do a substitution on that integral. So now we take this integral, and I made it in red so we can distinguish, it's x divided by 1 plus x squared. That looks like a substitution problem. U is 1 plus x squared. Du is 2x dx. But I don't see a 2. So I create the 2 and remove it. It's a product, so 2 times 1/2 cancels out to get us back to where we were. So everything is rigged up, ready to go. Remember, when you do a substitution problem, you rig up everything and then switch over to use. So then you're here. So here is the original problem. Sorry about that. My wife came in and asked me a question about our Washington, D.C. trip, and I forgot where I was. Anyway, coming back to this, you created a 2 and you removed it. So then you're ready to switch everything over to use. So you have 1 over u du, because the 2x dx is the du. Here's your 2x dx. That's the du. And the 1 plus x squared is down here. So you have 1 over u, you have 1/2. So that's 1/2 log absolute value of u plus c1. Again, I'm being very careful about the constants. Equals 1/2 log absolute value of what u was, which was this, plus c1. Now we go back to the original problem, which was arctangent. And we have the original statement, what we had. And now all we do is we take this integral, which we figured out, put it in here. That's what the answer to that was. You have a subtraction here, 1/2 log. I don't need the absolute value in this case because 1 plus x squared is always greater than 0, so I don't have to worry about it being negative for any x. And then notice how the negative will distribute all the way to the c1, and so negative c1 is now c. So this is your final answer. And here's what Wolfram Alpha has to say about the problem. Integral of arctangent x. Well, they like to have the -1 notation. I don't, but so what? Okay, so x, arctangent x, check. Subtract, check. 1/2, check. They explain later below here that the log is a natural log, so that's check. X squared plus 1, check. Constant.